Hello, everyone. I'm John Hayter from the Department of Environmental Science at Stockholm University, and my talk is on a novel risk mitigation strategy for chemical spills impacting sewage treatment plants. My co-authors on this work are Marcus Frenzel from the Shopala Wastewater Treatment Plant and Dr. Matthew McLeod, who is my PhD advisor here at Stockholm University. The funding for this work is from an EU Horizon 2020 Marie Curie grant within the EcoRisk 2050 Innovative Training Network, and I'd like to extend a special thanks to all the staff at the Shopala Wastewater Treatment Plant for their help and for hosting me on a secondment. So the Shopala Wastewater Treatment Plant is located just outside of Stockholm. It is a partnership of 11 suburbs in the Stockholm metro area. It's the third largest sewage treatment plant in Sweden, treating about 560,000 person equivalents, using a mixture of mechanical, chemical, and biological treatment before the effluent is released to the Baltic Sea. So here is a schematic of how a wastewater treatment plant fits in between the interface of humans and the environment. Upstream on the left here, we have Stockholm, where a range of businesses, industries, and homes are producing wastewater that's tunneled to the sewage treatment plant, where, among other things, microorganisms are used to help treat the water by breaking down various pollutants in it before that treated effluent is released into the Baltic Sea. Upstream, however, at various homes and industries, a lot of chemicals can be used. Now, as these chemicals are being used, small amounts of them make their way down the drain into the sewage treatment plant usually, and usually that's not a problem. However, you can have instances where a large amount of chemical can be spilled at one time, and depending on how toxic this chemical might be and how much is spilled, it can cause what a toxic shock to the microorganisms at the plant, where potentially a large number of them are killed, and that will decrease the treatment efficiency of the sewage treatment plant so that the outgoing effluent from the plant is not as treated as it usually is, which can potentially cause damage to the environment. Now, the Shopala Wastewater Treatment Plant is concerned about something like this happening, and so they would like to know which chemicals used upstream could result in damage to the sewage treatment plant if they were to be spilled. To answer this question, we need to know three pieces of information: what chemicals are used upstream and in what quantities, how toxic are these chemicals to the sewage treatment plant microorganisms, and what would the concentrations of these chemicals be in the biologically active regions if they were to be spilled. So to answer the first question, Shopala surveyed over 100 facilities upstream and asked them for a list of chemical products that they use on site, the chemical constituents or the ingredients of each of those chemical products, and also the amounts of chemical that they hold in stock or that they use annually. And a range of different facilities were surveyed, including vehicle washing facilities, power plants, as well as hospitals. And our final data set is made up of about 60 facilities and roughly 1,500 chemical products. So on to the second question: how toxic are these chemicals to the sewage treatment plant microorganisms? The process engineers at Shopala are interested in the minimum concentration that a chemical would have to have in order to have an effect on the microorganisms in the treatment plant. So our focus for this work is on the activated sludge tanks and the anaerobic digesters, but the results I'll be showing you here are really just for the activated sludge tanks. The European Chemicals Agency, or ECHA, provides a large amount of chemical data on chemicals that are registered for use in Europe. One of these pieces of information can be a predicted no effect concentration, or PNEC value, for sewage treatment plant microorganisms. And these toxicity values can be derived in a variety of ways, including the activated sludge respiration inhibition test. And this provides an estimate for the maximum concentration that a chemical could have within a sewage treatment plant before it would have a negative effect on the microorganisms. And we collected PNEC values for over 4,000 chemicals from the ECHA website. So on to the third question: what will the concentrations of the chemicals be in the biologically active regions if they were to be spilled? If we come back to our schematic of how Shopala fits in between Stockholm and the environment, we can talk about these high-end exposure scenarios, or a tier 1 risk screening that we can conduct. If we consider all of the chemicals that are used upstream, and then assume all of the masses are spilled down the drain and all of that chemical makes its way to the Shopala sewage treatment plant. Once inside the plant, we can assume that all of the chemical makes its way directly into the activated sludge tank. Now, before we can make an estimate of what the risk of this chemical might pose to the plant is, we have to talk about what the actual toxicity data we have. So for a chemical product, it is often made up of a number of constituent chemicals. It's effectively a chemical mixture. We only have toxicity information, however, for the constituent chemicals rather than the actual chemical mixture. So for this first pass of risk assessment, we can only calculate the risk of these constituent chemicals. We do this by taking the mass of the chemical just based on its percent contribution within the chemical product, divide that by the volume of the activated sludge tank to estimate what the concentration would be in the sewage treatment plant, and then normalize all of that by the P-NEC value or the toxicity value. And when we do this for all of the chemicals that are used upstream of Shapala, we get a plot that looks like this, where on the x-axis we have the high-end exposure concentration of these chemicals within the activated sludge tank, and then on the y-axis we have the potential risk that each of these chemical poses to the plant. Now, a risk value that is equal to or greater than 1 is indicative of that chemical potentially having a negative impact on the microorganisms of the plant. And what we can see from here is that the vast majority of chemicals that are used upstream of Shapala don't pose a risk value equal to or greater than 1. And that's really pretty good news. However, we can see that there are some chemicals that pose risk values equal to or much greater than 1. And so if we take a closer look at these, let's say just the top 10, we can derive a prioritization list of chemicals and the facilities at which they are used that Shapala can then use to facilitate communication with those upstream facilities to ensure that the usage and storage of these chemicals is done in such a way that mitigates their risk for potential spilling down the drain and, of course, contamination of Shapala. Now, these risk values are just for the constituent chemicals, but what about the risk of the full chemical product? So again, we don't have information on how toxic this mixture of chemicals is, but we can do the next best thing simply by adding together the risk values of each of these constituent chemicals. So this was the plot of the risk from constituent chemicals. And when we sum up the risks on a product basis, we get this plot, where again on the y-axis, we have now the summed potential risk for these chemical products. And we can see that the story hasn't really changed that much. For the vast majority of chemical products, the risk value is still far below 1. However, for those with risk values above 1, we can derive a prioritization list for further information gathering. So some limitations about this analysis is that there's quite a bit of uncertainty surrounding the upstream chemical masses, and also those P-NEC toxicity values. Wasn't actually able to get into that uncertainty here. Also, for a large number of chemicals upstream, about 40%, we don't have P-NEC values from ECHA, and so we cannot derive an estimate for the risk that those chemicals pose. Also, this is really a simplified risk screening. This exposure scenario is very high-end, potentially unrealistic, and more information gathering is needed to help try and refine these exposure estimates. So one thing we are doing towards that end is we're taking our tier 1 risk screening and refining that with a tier 2 risk screening, where we take into consideration the fate that the chemical might have within the plant. To do this, we are developing an equilibrium steady state fugacity model, primarily focused on the primary sedimentation tank, and a schematic of this is shown here, where we have chemical coming into the primary sedimentation tank. Within our model, then we can estimate how the chemical will partition between the solid and the water phase, as well as the water and the air phase. And once we have this, we can make a simplifying assumption that all of the chemical in the water phase goes to the activated sludge region, all of the chemical in the solid phase goes to the anaerobic digester, and then all of the chemical in the air phase just gets removed from the system. This is, of course, a simplified assumption. Within the primary sedimentation tank, the separation isn't perfect between the water phase and the solid phase. But again, this is just a slightly more refined risk estimate than from our tier 1 risk screening. So these chemical masses that are going out to the activated sludge, the anaerobic digester regions, those chemical masses can then be used to estimate risks for those individual regions. That chemical fate model is currently being finalized. Also, Jerome Scullin, who is a master's student at KTH here in Stockholm, is conducting simulated chemical spill dilution measurements, which will help us further refine those chemical exposure estimates by helping us understand how a chemical that is spilled down the drain at a facility upstream might dilute in the tunnels as it makes its way to Shapala. Also, we are developing an open source tool that can be used by other sewage treatment plants for free to help them conduct upstream chemical risk screenings. Now, this tool is very much still in development, but our draft name for it is the Rapid Assessment of Vulnerability from Emissions Upstream, or the Ravenstream tool. And what this tool might look like is a user would be able to input an Excel file that contains information on the facilities that are upstream, the chemical products that are held on hand, as well as the masses of chemicals and the constituent ingredients that are in that. The user would also have to input some simple plant facility information like the activated sludge volume, anaerobic digester volume, and then make a selection about what kind of tiered risk screening they would like. And once they start the processing of the tool, all of the chemical toxicity information that I was showing you, the chemical fate model, and the overall analysis will be applied to their upstream chemical information, and returned to the user will be a prioritization list of chemicals that are upstream based on the risk that those chemicals pose, as well as some visualizations of the chemical risk from chemicals used upstream. We would hope to have a first version of this tool online either by the end of this year or sometime during 2022. So the take-home messages are that we developed a method to prioritize risk to sewage treatment plants from upstream chemical spills. This will help facilitate communication and chemicals management between the sewage treatment plant and these potentially high-risk facilities. And this online tool that we are developing will aim to provide a streamlined risk screening for free to other sewage treatment plants who are able to gather the necessary upstream chemical data. And with that, I will thank you very much for your attention, and I'd be happy to take any questions virtually during the IWA conference.